Hi everybody. Today we're going to look at Chapter 5, the applications of derivatives. So as you already know, derivatives can be used to find maxes and mins of a function. We talked about an object being thrown up into the air and how when it's thrown up into the air, at some point it has to stop in its y direction to come back down. So when we look at a curve, we can find a max or a min when the slope is 0. We didn't talk about that too much, but in Chapter 5 we're going to look a little bit more into that. We're also going to look at optimization. We can use calculus to figure out what's the minimum surface area for the maximum volume of something, and we can solve other problems like that. So our first thing we have to consider here is a couple definitions. We have extreme values. Those are going to be the max or min of a function. The maximum is just the greatest point of the entire function. The minimum is just the minimum point of the entire function. We're going to define them in such a way that it says, let f be a continuous function on the interval with domain D. The absolute maximum says f of c is an absolute maximum if and only if. And sometimes in your notes we just write IFF as a little shorthand. It means if and only if. F of x is less than or equal to f of c for every x that exists in the domain D. Okay, so you'll see this too. The upside down A means for every, and you don't really need to know this now, but if you were to see a backwards E, it means for some. Okay, the idea is if we want to consider every single x, we use the upside down A. If we want to say at least one x, we use the backwards E. And this little curvy E is an epsilon. That's just going to mean it exists in the domain. The way that we're going to define the absolute maximum of this function is to say, let's check that point. Is that point less than or equal to, greater than or equal to every other point? No, it's not. I have this point that I can check that's greater. Is that greater than every single point? No, I can check this point that's greater. That point is the highest point, so there's no other point on the entire graph that is greater than it. There's one point that's equal to it, and that's itself, f of c. So that must be the maximum. And the minimum is just the opposite definition. Example 1, finding the extreme values. We want to look at just the interval negative pi over 2 to pi over 2 of sine of x and cosine of x. Well, hopefully we have an idea of what those look like, but we can graph those as well. So let's consider sine of x. From pi over 2, from negative pi over 2 to pi over 2, it's going to be from this point here to this point here, if we're considering radians. So I know that the minimum is going to be this bottom point. Consider finding the extreme values of the two functions, sine of x and cosine of x, on the interval negative pi over 2 to pi over 2. So hopefully by now you have an idea of what the graph of sine of x looks like. The graph of sine of x goes something like this, something like that. And this point here is negative pi over 2 to pi over 2. So the absolute maximum point on this interval is going to be this point right here, pi over 2 comma 1, or sorry, So the maximum is pi over 2 comma 1, and the minimum is negative pi over 2 over 1. So the reason why that is because there's no other point that's lower than -1 on this interval. So we're only considering the domain that was given from here to here. And on that interval, there's no point lower than -1, and there's no point greater than +1. If I extended the domain to all real numbers, the graph would keep fluctuating, and I would have a bunch of maximums and a bunch of minimums. But that's why we restricted the domain. It's a little bit easier to solve this problem. Cosine of x, however, from -π/2 to π/2, just looks like that. Because the graph is going to continue to go up and down forever. But this point here is 0, 1. And this point here is -π/2, 0. And π/2, 0. So in this case, there's actually two minimums because our definition, the definition for a minimum is f of x is greater than or equal to f of c. Since it includes or equal to, that means that I can have more than one minimum. So in this case, we have two minimums. So the maximum in this problem is 0, 1, and the minimum is -π/2, 0, and π/2, 0. And that's it for that problem. We just had to find all the extrema. Extrema is just another word for the maxes and mins. So we had to find all the extrema on the given function on the interval -π/2 to π/2, and we did that. All you have to do really is just look at the graph in this problem. We haven't talked about the calculus yet to find this. So let's consider a different kind of problem here. Let's look at 4 minus x squared on these different intervals, and we'll talk about how to find all the different maxes and mins on those intervals. So if I consider -∞ to infinity, hopefully you'll realize that it has one max and two min, because parabola. If I consider the function, it was 4 minus x squared. That's telling me that the y-intercept is 4, because if I plug in 0, I'd get 4 here. And it's a negative parabola, because it's -x squared. So this is exactly what I expected it to look like, but sometimes it's just nice to look at the graph and not just know what it's going to look like. So on the interval -∞ to infinity, it's pretty obvious that the maximum is 4. I'm going to say the point was 0, 4. And the minimum, well, the graph continues to go down towards -∞. So since the definition of a minimum says that it's the lowest point, there is no lowest point. No matter what point you pick, I can pick a point that's lower, so there is no minimum in this problem. Oops. There's no minimum. Now let's look at -2 to 2. -2 to 2 is just going to be this interval where the graph is at or above the x-axis, from -2 to 2. So in this case, there are two minimums and one maximum. The two minimum in this case are at the endpoints. -2 squared, or 4 minus -2 squared is 0. So in this case, the minimum, well, the max is the same. And the minimum is -2, 0 and 2, 0. Okay, now let's look at 0 to 2. This is a little bit different of a problem. because it's open. It doesn't touch the point 0, but it does touch the point 2. So if I were to look at this graph, it's this whole interval from 0 to 2. But it does touch 2, it doesn't touch 0. So the reason why that's important is because it touches 2. I know that that point is 2, 0. That's fine. That is the minimum. The problem is with the maximum. Let's say you pick a value for y that you say is the maximum. Let's say you say it's, well, we know that it's approaching 4 here. Let's say that you say that the maximum is 3.99. Well, I can get closer. The definition says that it is the absolute maximum point. I can say that this y value can get up to 3.999. And then you could say, well, I can get closer still, 3.99999. Okay, because we can always zoom in and get a little bit closer here. We'll never actually find the maximum value. So there is no maximum. Even though it looks like it's just about 4, it doesn't ever get to 4, so there's no maximum number. In calculus, we're kind of nitpicky there. So in this one, there's no max, and the minimum is just 2, 0. And again, it's just 2, 0 because there is no, the domain only goes from 0 to 2. Even though -2 was my minimum before, that's not in the domain in this problem. And part D is going to have no max and no min because of this problem we talked about before. It's never going to get close enough to either end. So there's no max and no min on this one. Because this one would have 2 open intervals, and you can never get close enough to that max, and you can never get close enough to that minimum. So now we're going to look at the extreme value theorem. So the extreme value theorem says if f is continuous on a closed interval a to b, then f has both a maximum and a minimum on the interval. This is just an existence theorem. An existence theorem just means that I'm checking to see if it exists. It doesn't help me find the max and min. It just says it has to exist. So here's what that's saying though. If I have 2 points and I connect them because they're continuous, there has to be some maximum or some minimum on those points. Whether the graph looks like this or like this, no matter what happens, I have at least one max and one minimum on this interval. A couple important words here are that it's continuous. Because if it's not if it wasn't continuous, then it doesn't have to be there doesn't have to be a maximum or a minimum anymore. Another important word is that it's closed. The closed means that it's got these brackets. We already saw if it's not closed, we have problems. Example D, for instance, had 2 open points. Since it's an open interval, I never touch the max or min. Now, it could have a max and min if it was open. I'm just checking. I'm saying if it's a closed interval, and if it's continuous, it has to have a maximum and a minimum. Even if the 2 points are linear, minimum, maximum. Even if they're horizontal, every point is both the minimum and the maximum because the definition of minimum and maximum includes equal to. So every single point on that interval would be both the minimum and the maximum. That's not going to come up very often. It's not a very interesting problem, but that's the definition. It just says that it exists because of the extreme value theorem. So now we're going to look at local extrema. This is a little bit more interesting. This is what we're going to look at in calculus. We will look at absolute extrema too. But a local extrema or a relative extrema is if there's a point C interior to the domain of a function, then f of c is a local maximum if and only if f of x is less than or equal to f of c for all values on an open interval containing c. We'll talk a little bit more about that in a second. The minimum is just the opposite. Same thing, but the value of c if and only if f of x is greater than or equal to f of c. So let's consider what that looks like. Let's look at this cubic function here. You can all see that this is a local maximum and this is the local minimum. There is no max or min on this function from negative infinity to infinity because the graph will continue up towards infinity and down towards negative infinity. So the reason why this is considered a local maximum is because if I set a domain around it, I can pick the open interval. It can be very small. I could just say from this point to this point, I'm just going to check every point around it. And if every point around it is lower than it, it's a local maximum. Okay, same thing here. It doesn't matter how small your interval is. It's pretty easy to see that I have a wide range of intervals. But even if I just say from here to here, this point is the minimum. This point right here is the minimum. Okay, that's all the definition of a local max or min is. That's the formal definition with calculus. All you have to really look for bumps. If you see a bump, it's probably a max or a min. So now we're going to look at theorem 2. We have a lot of theorems here. So the reason why I have so many theorems is because we need these definitions and these theorems to march forward with our actual calculus. We can't justify our math until we show that everything is in its proper place. Now let's consider theorem 2. If a function f has a local maximum or minimum value at an interior point c of its domain and f prime of x exists, then f prime of c equals 0. All that's saying, if there's a max or a min, let's consider the previous graph. If there's a max or a min, we say that f prime of c equals 0. Well, that should be pretty obvious. Just like in our problems where we threw the ball up in the air, at some point, the rate of change has to be 0. The slope of this graph at the maximum is 0. It's increasing, and then it turns to 0, and then it starts decreasing. So it's just saying at the maximum or at the min, the slope is 0. Now I did write that the converse of this is not always true, because we can have a slope of 0, and it doesn't have to be a max or a min. A common example of that is y equals x cubed. If you look at 0, the slope is actually 0. Even though there's no maximum or minimum there, the slope is 0. Because if you take the derivative, you get 3x squared. If you plug in 0, you'd find that the slope is 0. So even though f prime is 0, there isn't a max or a min. But if there is a max or a min, it has to be 0. And I kind of just glossed over this word converse like you remember it. Converse just says we switch the order. Instead of saying if there's a local maximum, then f prime of c is 0. The converse would be that if f prime of c is 0, then there's a local max or min. That's not true. So a critical point is going to be any point where f prime is 0. So that's what I was just talking about. Not every critical point is a max or min, but the max and mins can only exist at critical points. So the way we're going to solve this is by finding those critical points and then checking to see if they're maxes or mins. We can say here extreme values can only occur at critical points, or they can also occur at endpoints. If we look back to these problems here, they frequently occurred at the endpoints if there was a restriction on the domain. So now we want to look at example 3, finding the absolute maximum or minimum of f of x equals 2/3 on the interval -2, 3. Now, if you are allowed to use the calculator on this section, it would be a good idea to just look at the graph and figure out what it looks like. If you couldn't figure that out, we do know that this is x to the 2/3 power, so it is going to look something like cubed root of x. But let's just take a look at it real quick. X to the 2/3. Okay, that's a weird looking graph there. So I can see that there is a minimum here. I can also see, oh, I glossed over something in the definition. It also says, or where f prime doesn't exist. If you can see here, if we look at this graph, f prime clearly doesn't exist at 0. So I do have to check that point when I do my analytical analysis. But I am going to check f prime equals 0 because that's clearly the minimum. Just looking at this, I can tell that it's not going to have a maximum. Oh, actually, it will have a maximum because we're looking on the closed interval -2 to 3. So it has to have a maximum and it has to have a minimum. -2 to 3, I can tell that there is going to be a maximum at around 3 comma f of 3, and there's going to be a minimum at 0 comma 0. But I do want to find that analytically. I just wanted to know an idea of what I expect the maximum and the minimum to be before I get started. So I graphed this and saw that my max is going to be around x equals 3, and my minimum is probably going to be 2. So let's actually do the math here. The way that we find this is by finding the critical points. That again is where f prime is 0 or where f prime doesn't exist. So let's find f prime. X to the 2/3 power, we're just going to use the power rule here. F prime of x equals 2/3 x to the -1/3 power. Just use the power rule to find that. So I want to find when does that equal 0. When does f prime equal 0? So I have 0 equals 2/3 x to the -1/3 power. Actually, let's rewrite that. Let's rewrite that as 0 equals 2/3 x to the 1/3 on my denominator. Now, the way that I would solve this, since I have x's in the denominator, I could find the zeros by setting the numerator equal to 0, because 0 divided by anything is 0. But there's nothing in the, that could be 0 in the numerator. So this graph has no zeros. I'm not surprised by that, because I didn't see any points where the derivative existed where the slope looked like it was 0. There were no visible max or mins. If we remember, it looks something like this. So I can try to find when the derivative doesn't exist. So when it wouldn't exist is when you're dividing by 0. So I could set the denominator equal to 0. To find when it doesn't exist, we're going to say 2/3 x to the 1/3 equals 0. And this finds when the graph doesn't exist. Well, I could multiply by 3/2. I get 0 equals x to the 1/3. And the only point where it's not going to exist is when x equals 0. I mean, if you want to solve this, you could cube both sides. 0 cubed is 0. The point where it doesn't exist is x equals 0. And that's consistent with my graph. I saw this cusp at 0, 0. So my minimum, I have to check this point here. I have to check this critical point. I also have to check the endpoints. So I'm going to find all of those values. I'm going to find f of 0, because that was my critical point. I'm going to also find f of -2, because that was one of my endpoints. I'm going to find f of 3, because that was also one of my endpoints. Once I find those, I'll know my max and my min. F of 0 is clearly going to be 0. 0 to the 2/3 power equals 0. Let's also look at -2 to the 2/3 power. 2/3 power is approximately 1.58740. It is positive because I'm squaring it. And let's also look at 3 to the 2/3 power is about, let's say 3 to the 2/3 is about equal to 2.08 0, 0, 8. So my maximum is this greatest value, 2.808008, and my minimum is 0, 0. So to answer the question, find the absolute max and the absolute min. The max is 3, 2.08, 008, and the min is 0, 0. And we could have really done that without even looking at the graph. If I would have just followed the rules, since f is continuous, it has to have a maximum and a minimum, and the max and min can only exist at critical points. So if I were to just check the endpoints and check the critical points, that would have been my entire answer. That would have been the max and the min. So now we're just going to rewrite f of x here so that I can use the chain rule. So it's important that we write f of x, not f prime, or just equals, because it can get confusing. One of these steps we are going to take the derivative, so you need to write f of x when we're rewriting it, and then f prime when you're taking the derivative. So we're just rewriting this as 4 minus x squared to the negative 1/2 power. So now that I have it written like this, I can use the chain rule to simplify this, or to take the derivative. So I have f prime of x equals negative 1/2 times the quantity 4 minus x squared. And I subtract 1 to get negative 3/2 here. And then I'm going to multiply that by the derivative of the inside, which is negative 2x. So now I'm going to simplify this as much as I can. I have negative 2 times 1/2, those cancel. I'm going to rewrite the negative power so that it's just one simple fraction. So I have f prime of x equals, also negative times a negative is positive. We can get rid of that. We just have x over 4 minus x squared to the 3/2 power. So now I want to find the critical points, so that's when the derivative is 0. So now all I have to do is substitute, so now all I have to do is substitute 0 in for f prime, and we get x over 4 minus x squared to the 3/2. Again, my critical values are when f is 0 or when it doesn't exist. So when the numerator is 0, that's going to be my first critical point. That's when the function has a 0. X equals 0. Oh, it's already done. Now I have to find when the denominator equals 0. So these are going to be the points where it doesn't exist. So these are the zeros here. And then these are the points where it doesn't exist. It's when 0 equals 4 minus x squared to the 3/2 power. Well, I can just raise this to the 2/3 power on both sides, and that gets rid of that 3/2 power. So let's just raise this to the 2/3 power, 0 to the 2/3 power. We get 0 equals 4 minus x squared. And that'll be 0 equals 2 plus x and 2 minus x. That means that my critical points are going to be plus or minus 2. And that looks pretty consistent with my graph. It looks like there may be a vertical asymptote at 2 in my graph, so it makes sense that there's a critical point there. It also looks like there's a minimum at 0, so that's consistent with my graph. I have to consider whether those points are maxes and mins. Now, I know that 0 is a min, and that -2 and 2 are both undefined. They're probably points where the graph doesn't exist, but I have to show that analytically. Because sometimes we'll have a problem where you're not allowed to use your calculator and you're not allowed to look at the graph. So, we're just going to consider the critical points here. The critical points where x equals 0, -2, and 2. So now I'm just going to plug that back into my original equation, 1 over the square root of 4 minus x squared. But I'm going to plug in those critical values. So let's find f of 0, 1 over the square root of 4 minus 0 is just going to be 1/2. Let's find f of -2. F of -2 is 1 over the square root of 4 minus -2 squared is going to be 1 over 0. So it does not exist. And f of 2 is going to be the exact same thing, 1 over the square root of 4 minus 2 squared, which is 1 over 0. It does not exist. So I do know that 1/2 is probably a max or a min, but at this point, -2 and 2 don't exist. So I know it is going to be continuous. If I look at the graph here, or the function, it will be continuous from -2 to 2, but there is a problem on the actual endpoints. So now I just have to look at, is this point 1/2 a max or a min? Well, since it's either the greatest or least, since it's either the highest value or the lowest value on my point, on my graph, I can plug in any other number in that range from -2 to 2 to find out if 1/2 is a max or a min. So just to check here, and this is again, assuming I couldn't look at the graph to figure this out, let's figure out what f of 1 was. F of 1 is 1 over the square root of 4 minus 1 squared, which is 1 over the square root of 3, which is approximately equal to 0.57. And since that's greater than 1/2, we know that 1/2 is a min. Okay, so the original question asked us to find the extrema. We'll say 0, 1/2 is a minimum, and there's no relative maxes. And there's no absolute maxes either. So that's it for that problem. It just said to find the extrema, so that's what we did. Now we're going to look at an example of a piecewise function. So I'm going to do a quick sketch of what this piecewise function would look like before we get started, and then we'll approach it from there. So the easy part is the linear part. X is less than 1, and that's x plus 2. So it's going to look something like this. Going to be a graph like that. It's going to be linear. Sorry, that's not perfect, but it's going to be linear with a positive slope and a y-intercept of 2. That's x equals 2 right there. Now we're going to look at 5 minus 2x squared. 1, 2, 3, 4, 5. The graph of this is going to look something like this. And that, again, is not perfect, but we have a line on the left and a parabola on the right. and they do touch at 1. The way I could check that is just 5 minus 2 is 3, and 1 plus 2 is 3. I know that they will both, f of 1 in both cases is 3. So it's going to be continuous. And it is equal here. It is, x is less than or equal to 1, so it will be continuous. When it says to find the extreme values, I do have a pretty good idea that the extreme value is going to be right here, just because of the nature of both these graphs. This is a downward facing parabola and x plus 2. So this is going to have, x plus 2 is going to have no critical values. Let's find f prime of the top half here. That's going to be negative 2x squared. And that is if x is greater than or equal to 1. And it'll only take a second, but f prime of x is 1 if x is greater than 1. The only critical value would be if f prime is less than or equal to 1, because on greater than 1, there is no x to solve for. You would just have 0 equals 1, there's no critical value. The only critical value for x is greater than 1 would be x equals 0, but since x equals 0 is not in this half of the graph, it's not a critical value. If I were to draw this parabola, it would look something like this, and the critical value would be here, but that's not what the graph looks like there. It's this line, when x is 0, it's touching this point 2. So this is not a critical value either. So now we have to only consider what if the derivative does not exist. Critical value right here, because the x equals 1, there's a cusp. Now we just have to find out what that maximum is. We actually already found that out. That is f of 1 equals 3 is the maximum. Max is 1 comma 3. And it's 3 in either case. If I plug in 1, well, I do have to plug in 1 in the top part here when x is less than or equal to 1, because that's where 1 is. But in both cases, it is 1. I need to plug it in both sides to make sure it's continuous, to make sure that there's a maximum there. If it's not continuous, it's not considered a maximum. Okay, and there's no min in this problem. Finally, we want to find all the extreme values of f of x equals natural log of x over 1 plus x squared. So again, we're going to find the extreme values. Let's look at what the graph looks like first. I'm going to find the natural log of the absolute value of x over 1 plus x squared. So the natural log of the absolute value of 1 plus x squared looks like a folded up book or something like that. Looks like we have a max at around 1 and negative 1. And it looks like we have a min. I'm not sure what that point is. It doesn't look like it's quite at 0, but I would guess that it probably is at 0. Since the graph looks relatively symmetric, I'm thinking that the calculator probably is just a little confused here. Let's zoom in just to get a better idea. Yeah, it looks like that's at 0. Let's do our math now to figure out if that's actually true. So the first thing I want to do is find the derivative of f of x. And if you don't remember, the derivative of f of x is u prime over u. So let's do u equals x plus 1 over x squared, and u prime, I'm going to have to use the quotient rule for this one, low d high, minus high d low, over low low. And I could expand that, but I'm not going to, because I think that I could probably most of the time I can get something to cancel. I'm going to see if I can simplify this just a little bit more. U prime is 1 plus x squared minus 2x squared over 1 plus x squared. And this simplifies to 1 minus x squared over 1 plus x squared squared. I'll leave that like it is right now because I don't think it's going to be worthwhile to try and simplify it anymore right now or expand it or anything like that. So now that I know u and u prime, I'm going to just plug that into the equation. I have u prime, which is 1 minus x squared over 1 plus x squared squared all over u, x over 1 plus x squared. Since I am dividing fractions here, I should mark that this is f prime of x. Since I am dividing fractions, I can rewrite this as multiplying by the reciprocal. 1 minus x squared over 1 plus x squared squared times 1 plus x squared over x. These two cancel, and I'm left with 1 minus x squared over x times 1 plus x squared. Now it does say to find the extreme values. Remember, the extreme values are the points where x either is 0 or does not exist. So let's find those real quick. Let's find when u prime, no, that's not what I want. So let's find the extreme values now. That's going to be when 0 equals 1 minus x squared times x over 1 plus x squared. So the points where this is 0 is going to be when the numerator equals 0. So 0 equals, this is the zeros, is at 1 plus x, 1 minus x, since that's the difference of squares. So the 2 points where this is 0 are when x equals plus or minus 1. And then let's find when it doesn't exist, does not exist, when the denominator equals 0, because remember we can't divide by 0, at x over 1 plus x squared. So it definitely does not exist at 0, but it also doesn't exist, oh actually it doesn't exist at x equals 0, and we can also try to find when 1 plus x squared equals 0, but there's going to be no point where that happens. If I subtract 1 on both sides, x squared cannot equal negative 1, so the critical points are going to be 0 and plus or minus 1. So now that I know the 3 critical points, are x equals 0, 1, or negative 1. I'm just going to substitute those in to find if they're maxes or mins. I lost the absolute value there. That's fine. So now I'm just going to find the absolute, I'm going to plug in the critical points to find if there's any relative maxes or mins. So let's find the natural log of, let's find f of 0, and we get natural log of 0 over 1 plus 0 squared, natural log of 0, undefined, so there is no max or min here, because Even though on the graph it looked like there's a minimum at 0, the natural log of 0 does not exist. So there is no max or min there. It's not continuous. Let's also consider f of 1 is the natural log of 1 over 1 plus 1 squared is going to be natural log of a half. Approximately negative 0.693,147. And let's find the absolute value of f of negative 1 now. We're going to have negative 1 over 1 plus negative 1 squared, which will be natural log of absolute value of negative 1/2. But since it's the absolute value, it will be symmetric, and this is going to be the exact same value of negative 0.693147. Now, it did say find all the extreme values. I know that these are the extreme values, but I don't know if these 2 points are maxes or mins in this problem. So I am going to have to find one more point. Any other point would work. And now I just have to check any other point that would exist because these 2 points are their maxes or mins. So any other point would tell me. If it's a lower point, then it means that these 2 are maximums. And if it's a higher point, then it means that these 2 are minimums. So let's just check that real quick. Any other point would work, so let's just try. F of 2 is natural log of 2 over 1 plus 2 squared. That point is negative 0.91. And since that point is lower, that means that these 2 points that I have are maximum. So since that point is lower, my 2 maxes are -1, negative 693, negative 0.693,147. And negative 1, negative 0.693,147. So those are the 2 absolute maxes. There are no minimums. And I know that because it doesn't exist at the point where the minimum would exist. The critical point is at the natural log of 0. Since it doesn't exist there, there is no max or min there. Thank you for watching again. Remember to complete your assignment on the Google Classroom.